and I've got another fun experiment to show you today. And thank you to one of my students, I think it was Adam, who asked me to make this video. Today, what we're going to look at is the Doppler effect. So, the Doppler effect is something you probably all know about. Have you noticed when a really loud motorcycle drives past you at speed, you get an interesting sound? The engine sounds like this as it goes past. It goes neee as it drives past, and the next one does the same. Of course, the sound gets louder as it comes towards you, and it gets quieter when it goes away. There's a change in amplitude, but because of the neee effect, what's also happening is the frequency seems to be higher when it comes towards you, and the frequency goes down when it drives away. So what's going on here? But it's also interesting to ask, what does the motorcycle driver hear? They clearly don't hear meow every time they drive past someone. They just hear a constant note. So what's interesting is what you hear depends on where you're positioned. The position of the observer of the sound is important. So let's see if we can simulate this in the classroom. I've got myself a little buzzer here, and what I'm going to do is switch the buzzer on so it's like the motorcycle engine, and then I'm going to swing it around my head and make sure that it gets closer and further away to the microphone on the camera. So that's like the person on the side of the road listening to the motorbike. So here we go. And there we go. I'm going to swing it around past the microphone. And what I hope you hear is the meow effect as it's going past the microphone. But now let's see what it sounds like from the point of view of the person on the motorcycle. So of course the motorcycle engine travels with them, it's not moving towards or away from them. And you'll notice that the frequency of the note stays constant. There are a number of other ways to demonstrate this as well, and one of them is literally to switch on the buzzer and to move it backwards and forwards towards the microphone of the camera. And that's the same effect as if the motorcyclist is driving towards you and away from you. The buzzer isn't changing the note that it makes, it's the movement relative to the observer that's important. So, as I said earlier, this effect is called the Doppler effect, and it's named after Christian Doppler, who first formulated what was going on in about 1840 in now what is modern Austria. He didn't live very long, in fact, he only lived until he was 49, but he did some great work. And what's interesting was he noticed this effect with light from binary stars. And light, as you know, is a wave, and sound is a wave, so the reason for the Doppler effect must be something to do with the way waves behave. It can be quite fun to show the Doppler effect on a really big scale. So, if I drive the car along and I'm stationary with respect to the car, in other words, I'm inside it, if I press the horn, you hear the note, and the note stays at a constant frequency. But now look at things from the point of view of an external observer. If I drive past the camera and hit the horn, you'll hear the frequency go up as I get closer and then go down as I drive away. And that's the Doppler effect. There is a story of a brass band being put on a flat carriage of a train and driven very quickly through a station. And if you think about it, the musicians playing on the train are stationary with respect to each other, so they hear the music being played at the right pitch, at the right frequency. But you get a completely different effect if you're standing on the platform of the station as the train rushes past. As the train comes towards you, the musicians seem to be playing at too high a frequency, and as they go away from you, the frequency seems too low. It's as if they've lost their tuning. But just as they're level with you, everything sounds okay. So, now for an explanation, and it's not a particularly easy one. I've set up a couple of springs in front of me here, and what I'm trying to represent is here's an object giving out sound waves, and the sound waves are going in opposite directions. And if you're stationary with respect to the object, the sound wave spacings, in other words, the wavelength, is the same in both directions. But if you're positioned over here and the object producing the sound moves towards you very quickly, what happens is it gives out a sound wave, and then the next one is given out a little bit closer than it should be. So the waves are all bunched up. The wavelength gets shorter and the frequency goes up. But of course, if you look at this end, if the object rushes away from you, the sound wave is given off, and then the next one is given off just a bit further away than it should have been. So the waves are stretched out, and the wavelength is longer, and therefore the frequency is lower. And again, this is the Doppler effect. So the springs show nicely how the Doppler effect works. If you're stationary with respect to the thing that's producing the sound waves will be of the right wavelength and the correct frequency. But if it's moving with respect to you, here is the neee-ow effect. High frequency, low frequency, as the object rushes past you. So, if you study physics, it's really important to know a bit about the Doppler effect. It has masses and masses of uses. Everything from baby scans to look at the blood flow within the mother and the baby, through to checking if the universe is expanding. So it's a really powerful technique. Hope you enjoyed that video, and I look forward to seeing you again next time.